We have learned with double replacement reactions that in order for the reaction to actually happen, one of the products needs to be not aqueous. So that means that one of the two products needs to be either a solid, a liquid, or a gas. Liquid is fairly obvious to identify. Usually that's just water. Gas, those are going to be any of your molecular compounds or any of your diatomics. Solids, that's where this is going to require a little bit of work. So our job is to determine whether an ionic compound is going to be dissolved in water or if it will remain solid when placed into a solution. So we need to determine its solubility, the solubility of various ionic compounds. So solubility is the amount of given substance that can be dissolved into a certain amount of a solvent. Now substance, what that really means is solute. So solute and solvent, these are the two pieces that make up a homogeneous mixture or a solution. So a solute is the thing that is dissolved. Okay, typically it's a solid at the beginning, and then you add it to the solvent. The solvent is the thing that does the dissolving. Okay. And when the solute is fully dissolved in the solvent, that is when you get a homogeneous mixture or a solution. If it's not fully dissolved, if you still have solid particulate floating around, that's still heterogeneous. So when something dissolves, it goes through what is called a dissociation or an ionization process. Okay, so salt is a really good example of this. We know that salt dissolves in water. So this is not a chemical change, by the way. This is a physical change. We learned this back in Unit 2 when we did our physical and chemical changes section. Dissolving is a physical change because it is reversible. So this is not a reaction with water so much as it's just being mixed into the water. So if I take salt, just plain old solid salt, and I mix it into water, it's going to ionize or dissociate, which just means it breaks down into its ions. So we get Na1+ in the aqueous phase and Cl1- also in the aqueous phase, meaning dissolved in water. Notice I didn't make this Cl2, and it's not a gas, okay? These are ions. And what's happening here is that these ions are attracted to the water molecules. So I drew a water molecule up here re-explaining the polar nature of water, how the hydrogens are the partially positive side and the oxygens are the partially negative side. If I do that again down here, imagine that you have a whole ton of these sodium ions and chloride ions. Okay. Your sodium ions are going to be attracted to the negatively charged oxygen side of the water molecule because they are positively charged. And then your chloride ions are attracted to the hydrogen side. Okay, so this goes back to something we've discussed a few times, IMFs, intermolecular forces. So whether or not something dissolves is dependent on how attracted it is to the water molecules. Okay, so if the ions of a compound are more attracted to each other than the water molecules, they'll remain solid. If they like the water molecules, they will dissociate or ionize and result in an aqueous solution or a homogeneous mixture. Okay, so ultimately we can have three categories when we are talking about the solubility of an ionic compound. It can either be soluble, slightly soluble, or insoluble. It's more of a gradient. It's not so black and white. We are going to leave slightly soluble for AP Chem. We'll talk about that in AP Chemistry. There's other factors that determine just how soluble the middle ground is. We're going to stick to the extremes for now. So if something is soluble, that means it dissolves in water. And again, we're talking about ionic compounds right now. That means that they are aqueous. Okay. If something is insoluble, meaning its ions like each other more than they like the water molecules, it will remain in its solid phase. Okay. So again, only ionic compounds will dissolve in water. How do we know which ones? Well, we need to consult what are called the solubility rules. So I'm really sad to be teaching this unit online and not in person, because this unit has my favorite lab. And yes, I know I say it's my favorite lab every time we do a lab, but really this one's my favorite lab, where you guys would be able to do a whole ton of double replacement reactions and actually develop these solubility rules by yourselves by making observations. We don't get to do that. Very, very sad. It's okay. We're healthy. That's what's important. So the full solubility rules are on Classroom. I would recommend going and printing those out. I do not have a printer, so I got to write them down in my notebook because I'm super special. So these are the rules, okay? So up here we have a chart that shows us which compounds containing which ions are going to be soluble, and then another chart that shows us insoluble compounds. So if something is soluble, remember that means that that compound would be aqueous. Okay, so if I'm reading this chart, let's say I find a compound, let's just talk about NaCl, which we just dealt with. NaCl contains this sodium ion. All right, the sodium ion is going to be aqueous. All right, a compound containing a sodium ion is going to be aqueous with 0 exceptions. Okay, same thing for a compound that contains potassium or a compound that contains ammonium, NH41+. There's a few of these. So these guys right here, sodium, potassium, and ammonium, nitrate, acetate, chlorate, and perchlorate. You'll notice that there's nothing over here on the exception side. What that means is if a compound contains one of these 1, 2, 3, 4, 5, 6, 7, 8, one of these 8 ions, I was going to say anions, but there's some cations here, then you know it's going to be aqueous without even having to think about it. So these guys that I just highlighted yellow, I call these my alwayses, okay, which is a really super proper English word, okay? These are the alwayses. Anytime you see these ions, you know that that compound is going to be aqueous and will dissolve in water, okay, without having to think about it. Now we have some examples where they're usually going to be aqueous, but there are some exceptions. So the halogens get a little tricky. Chloride, bromide, and iodide are, if you have a compound that contains one of those 3 ions, typically it will be aqueous or it will dissolve in water unless it is bonded to a silver, a mercury 2+, or a lead 2+ cation. Okay, similarly with fluoride, okay, usually aqueous, compounds containing fluoride are going to be aqueous unless that fluoride is bonded to a magnesium, a calcium, strontium, barium, or a lead 2+. Okay, similarly, more exceptions with sulfate. So if we have an exception, if our compound meets the exception, like let's say we've got a silver chloride, normally compounds containing chloride would be aqueous, but since it's bonded to silver, that would make it actually solid and it would precipitate out of solution. Okay. Down here we have the opposite example where we have, here are the rules that determine insoluble compounds. So these, all these are anions. Anytime you see these anions, your brain should go, oh, that's going to be solid. But of course, there are exceptions. So for these guys, for carbonate, phosphate, oxalate, chromate, sulfide, and oxide, any compound containing these polyatomic anions, and these 2 are monatomic, will be solid unless one of these is bonded to either ammonium or a 1A metal. So that's sodium, lithium, potassium, those guys. Okay, so if our compound meets the exception, then it goes back to being aqueous. Same thing with hydroxide. Most hydroxides are solids. In other words, they do not dissolve in water unless that hydroxide is bonded to ammonium, a 1A metal, plus a couple others, calcium, barium, and strontium. So anytime that you are assigning phases with double and single replacement reactions, I would have these rules out next to you and constantly be referring to them. Okay. So again, you want to memorize the alwayses, and this is going to help us determine whether or not specifically double replacement reactions happen or not. So let's look at a couple of examples. So here we have sodium sulfate reacting with iron 2 nitrate. So before we even dive into the actual solving of the reaction, let's just see if these guys are aqueous or solid to begin with. So here, when I look at sodium sulfate, sodium is one of my alwayses. It's one of my ones that I just remember is always aqueous. Okay, so I don't even have to think about it. I know that compound is aqueous. In other words, it will dissolve in water. What that means is in my beaker, in my solution here, I don't have a solid sample of sodium sulfate. That means that I've got 2 sodium ions, okay, right, because there's 2 of them, and 1 sulfate ion. They have ionized. They are no longer bonded in a crystal. These ions are attracted to the water molecules and they pull them into solution. So it's just a bunch of ions floating around. Here, iron 2 nitrate. Nitrate is another one of my alwayses. I really enjoy saying that, so you're going to hear a lot of that. So I know that this one is also aqueous. So now I've got, in this solution, I've got 2 nitrate ions floating around and 1 iron 2 plus. Now obviously there's going to be billions upon trillions of them, but I'm just showing you ratio wise. Okay, so let's say that I take these 2 homogeneous solutions and I mix them together. The question is, does something chemical happen? Well, let's find out. So I'm going to do a double replacement reaction. My sodium and my nitrate are going to bond, NaNO3. Okay, and then my iron and my sulfate. So that's iron 2. So I'm going to make FeSO4. Okay. So now I have to go evaluate solubility. Well, here are my 2 alwayses bonded to each other. I've got sodium and nitrate. So I really shouldn't have to think about this. This is definitely going to be aqueous. Okay. And then I'm going to have to look at my solubility rules for iron sulfate because none of my alwayses are there. So over here I see that sulfates most of the time are aqueous. I want to make sure that iron is not an exception to that rule. Look over here. Do I see iron in my list? No, I do not. So this is also going to be aqueous. Okay. Of course we can go back and balance this reaction, which luckily just requires a 2 right here. So here's what that means. This was a double replacement reaction. I made 2 aqueous compounds, which per our notes last week means that there is no reaction. Nothing happens. Okay, but why? Because I was able to write formulas, so why isn't this a chemical change? Well, all of these things are aqueous, which means these 2 products are still just a bunch of ions floating around. So again, we've got 2 sodium atoms. Sorry, ions is what I should have said. I've got 2 nitrates. Dang it. That's what you love to hear. Your teacher saying, dang it. Okay, inspires a lot of confidence. And then over here, I've got an iron. And all of these things, all of these ions are just floating around in solution. Nothing has changed. Chemically, it's exactly the same. All I've done is taken those 2 solutions and mixed them together, which is a physical change. It's not chemical. So this is a double replacement reaction that I could set up, but nothing chemical would happen. All I would do is just mix the 2 solutions together. Okay, so that's the reasoning why a double replacement reaction needs to actually produce something that's not aqueous. Let's look at this example. We've got ammonium carbonate and iron 2 chlorate. So let's do the double replacement. We're going to make NH4 ClO3 and then iron 2 carbonate, so FeCO3. Okay, let's just go ahead and balance right off the bat. 2 of those and we're done. Okay, so now the first thing I want to do is look for my alwayses. Here's ammonium. I love it when I see ammonium. That means my job's going to be really easy. Here's a chlorate that's also an always, and here's the two of them bonded to each other. So without thinking about it, I know that my two reactants are going to be in the aqueous phase, as they will be, by the way, like 99% of the time. One of my products is definitely aqueous, and now I have to assess this iron 2 carbonate. Is this going to be aqueous? In other words, will it dissolve in solution, or will it fall out of solution as a solid precipitate? So you see I have carbonate. All right, that's on my chart over here. Carbonates are usually insoluble, and I want to make sure, is iron an exception? And no, it's not. Iron is not ammonium, and it's not a 1A metal. It's not an alkali metal. So what this means is I will indeed make a solid. So this reaction will happen. So here's what's happened. In this starting solution, I had a couple ammonium ions and a carbonate. In this other solution, and all of this was aqueous, these were all just ions floating around. Some chlorate ions and an iron ion, that's difficult to say. And all of these ions are in their aqueous phase, which means they're more attracted to the water molecules. So everything's fully dissolved. These are homogeneous mixtures. Okay, I take them and I pour them into one beaker. This time we have some chemistry happening. Okay, now these ammonium chlorate ions are still going to be aqueous. Okay, they still like the water molecules more. So I've got two ammoniums and I've got two chlorates. Okay, but now I have this iron 2 carbonate, which is forming as a solid. Okay, so I'm going to use my super awesome artistic skills. Okay, that is your iron 2 carbonate solid separating itself from the solution. Okay, and it has precipitated out of the reaction. So something chemical has happened here, whereas you can see nothing chemical happened up here. Now, if I do this reaction in real life, normally I'm not just going to see a clump of solid at the bottom. Remember we talked about this in our chemical and physical changes lab. You would usually observe an opaqueness or a cloudiness or a separation, color change, stuff like that. But if you let it sit for a long time, the precipitate would precipitate out of solution and would collect at the bottom of the sample. So that is how you identify the double replacement reaction has happened.